Hello, my name is Moses Ajay. I'm going to be presenting on food process technology FDT 300M, and I'm going to be focusing on heat transfer by conduction. At the end of this presentation, you will be able to explain the mathematical concept of heat transfer in food by conduction. And at the same time, you will be able to apply heat transfer equation to solve simple problems involving heat transfer in food processing via conduction. So heat transfer by conduction, you can see from this figure that heat transfer will depend on three different parameters. The very first one is the temperature difference between the two surfaces of the material. We have T1 and T2, and the second one is going to be on the area available for it to pass through. Now here we have this area here, so it's going to be affecting the rate of heat flow through this material. And finally, the thickness of the food. Now the thickness of the food is also very important because that's the distance the heat travels from one phase to the others. Now let's take note of the three parameters. We have the first one we have a temperature difference, and that is measured in Kelvin. We have heat transfer. We have the area for heat transfer, which is the symbol is A and is measured in meter square. And the distance the heat travels, this is X. That's the thickness of the material and is measured in meter. And we know we are talking about the rate of heat transfer. So let's look at what happened. Now the rate of heat transfer in a material will increase directly with an increase in temperature difference, and then secondly, an increase the rate of heat flow will also increase with an increase in the area available for heat transfer to pass through, and finally the rate of heat transfer will be inversely proportional to the thickness of the food material. What am I trying to explain here? Now, in the previous slide. Now, the rate of heat transfer is going to be a function of the temperature difference. So, the more the temperature difference, the more the rate of heat transfer. That's the very first thing, because temperature difference is like the driving force for the heat transfer. And secondly, the rate of heat transfer is going to be proportional to the surface area. If we have more of this area, you expect the rate of heat transfer to go up. And finally, the rate of heat transfer is going to be inversely proportional to the thickness of the food. Now you can see if we have a very thick material, that the rate of heat transfer it's going to affect the rate of heat transfer by making it to go down. Now if it is a thin material, you expect the rate of heat transfer to be more, so it's going to be inversely proportional. So take note of the three statements. The first one is saying that the rate of heat transfer Q is going to be directly proportional to the temperature difference T1 minus T2. And the second statement is saying that the rate of heat transfer is going to be directly proportional to the area. And finally, the third statement is saying it's going to be inversely proportional to the thickness of the food materials. So take note of these three equations. Now let's combine them together. Now if you combine the three equations together, this is what we're going to have. We're going to be having Q is directly proportional to A multiplied by change in temperature divided by X, which is the thickness of the food material. So we have this. Now we want to introduce a constant of proportionality K. So if you change your proportional sign to equality sign, you have your K, and our K is defined as thermal conductivity. Now K is the constant of proportionality, and it's defined as thermal conductivity. So I want you to please take note of this first equation, which says that our Q equals Ka dt over X. Please take note of that equation. Now, heat transfer by conduction. So we have this as our formula. Now, from here, we can have our K. Our K can be expressed as Qs over A change in temperature. How do I arrive at this? Let's look at this. So this is where, when you cross multiply this, you have Qs equals Ka change in temperature. Now we are looking for K, so we always go to put the side of the equation where our known variable to be at the left hand side. So we have our Ka change in temperature equal Qs. Now we can see here now that we can divide through by A T1 minus T2. When we divide both sides by that, so we have this. So when you divide both sides by A T1 minus T2, so A T1 minus T2 will cancel this, so we now have our K to be QS A, the QS divided by A change in temperature. So we can also find the unit of K. Now we know that our unit from the table I gave earlier, we know that the unit of Q is watt, which is the unit for measuring the rate of heat transfer. S is meter, and A is meter square. K is for change in temperature. So from there we can have our unit for our K to be watt per meter per Kelvin. So let's take note of the unit for K. Now let's look at another analogy for heat transfer. We are comparing heat transfer to Ohm's law. Let's look at this. Here we're going to be talking about the concept of thermal resistance. Now in Ohm's law there are three elements. We have the voltage, which is the driving force. We have the current, which is the flow rate of electricity around the circuit, and we also have the electrical resistance. Now this which is defined as R. Now our Ohm's law states that our I equals V over R. I'm saying that our current equals V, potential difference, over resistance. Now what that one is telling us is that our flow rate, which is the current, is defined as the driving force, which is the potential difference, divided by resistance to flow. Now let's take this one now to heat. For heat transfer, this is telling us that rate of heat flow, comparing the two equations, rate of heat flow will be driving force, which is the temperature difference, divided by thermal resistance to flow. Now the rate of heat flow, as we have said earlier, is Q. Don't forget that. Our rate of heat flow is Q, and our temperature difference is T1 minus T2, and our thermal resistance is RT. Now remember our equation 1 that says that our Q equals Ka change in temperature over S. Now you can see Q is this from equation 2 and Q is also this from equation 1. Now that shows that both of them are equal. Let's see if we can equate them together. So from equation 1 we have this, and from equation 2 we have this, and we can say they are equal together by the virtue of saying Q equals Q. So we can say that our T1 minus T2 over RT from equation 2 equals Ka T1 minus T2 over S from equation 1. Now we can see that T1 minus T1 minus T2 are common to both sides, so they can cancel out each other. So we have 1 over RT, Ka over X. So our RT will be X over Ka. Now how do I get this? From here we know that if you cross multiply, you have RTKA equals X. So when you divide both sides by Ka, you have Ka will cancel Ka from here, then Ka will be to this side of the equation as denominator. Now how do we get the unit of RT? Now the unit of RT is very simple. You know our X is in meter, our K has been given to us as watt per meter per Kelvin. So A is in meter square. So by the time you cross that one out, see M is going to cancel one M here, M square. So one of these M will cancel one M raised power minus 1, and the remaining M will cancel this one. So you can see K is raised power minus 1 in the denominator here. So when it goes up, the factor of minus 1 will disappear. So that's why we're having K over W. K over W is the unit of RT. And if you go in here, you can see that our RT is going to be changing temperature over Q. Now if you cross multiply, we take RT up. Can you see this? We take RT up. So our change in temperature K over Q will be RT, which means K over W will be the unit of RT. So that's another way of deriving the unit from the original equation for Q equals from equation 2. Now let's look at let's look at an example. So let's apply the equation we've gotten to a particular example. Now this is an example of a coaster which is constructed from a concrete of a thermal conductivity of 1.4, and it is the thickness of the material is 0.3. Now the inner temperature is 2, outside temperature is 24 degrees Celsius. Now they are saying that assuming no heat transfer occurs through the floor, estimate the rate of heat leakage into the store. And second equation say the heat leakage to be removed by refrigeration per week of operation. Now What are we giving? That to solve this problem, you need to look at what are you giving. This is what we are giving. We are giving a coaster. A coaster of the dimension. This is a 3 meter height, 4 6 meter here, and then we have inner temperature is 2 degrees Celsius and outside temperature is 20. Then the thickness of material of construction, which is the concrete, of thermal conductivity of 1.4 watt per meter per Kelvin, is given to us as 0.3 meter. That's the thickness. So please take note, this is per meter per Kelvin, so please take note of that. So to solve this problem, we know all these have been given to us, and we are also given the parameters to compute the area, the surface area. No, we want the question say calculate the rate of heat leakage. That they are asking us to calculate Q. So we are asked to calculate Q. We are asked to calculate Q, and we are given temperature difference. We are given K. We are given area, because yes, area is not given directly, but we are given the parameters to compute the area. So we know our K. We know we can know our A. We know our change in temperature. We want to find Q. So the equation that is required here is simply Q equals Ka, the change in temperature, over X. Now, because I mentioned earlier, we have been given parameters for us to calculate the surface area. Now, how do we calculate the surface area? This is very simple. Now, because we know we've been told that we should assume that there's no heat leakage at the floor. So all we need to do is to calculate all the areas for the walls, which is 3 times 4 multiplied by 2, because we have 2 of this. We also have 2 of this. We have 3 times 6 multiplied by 2, and we also have the roof, which is 6 multiplied by 4. So that is how we got the total surface area for heat leakage. The total surface area for heat leakage is area for the walls plus area for the roof. For the wall, we have this. For the walls, we have these two, this side, this and this. And for the roof, we have 6 multiplied by 4. So finally, we have our total surface area to be 84 meters squared. So we know that Q equals this from equation 1. You remember that? So substituting all that we've been given and the area that we computed into the equation, so we have our Q to be 7056 watts. Now this is K is given to us as 1.4. This is the area we just calculated. Change in temperature 20 minus 2, and the thickness is 0.3. So putting that one into your calculator, you have this as the answer for the rate of heat leakage into the store. Please take note, we do not include the area for the floor, because the question says assume that there's no heat loss. There's no heat loss through the floor of the cold store. So that's why we do not include area for the floor. We only include here we have an area for the roof and for all the walls. Now the second question says that we should find the heat leakage to be removed by refrigeration per week of operation. Now we've been able to find the amount of heat leakage into the store. We've calculated that, and if you look at the unit of this, the unit of this is joule per seconds. No, the unit of the watts is joule per seconds. Now what is this one telling us is that 7056 joules of heat energy is removed in every second. So that's the implication of that computation. We know, don't forget that our words can also be in joule per seconds. So it makes it more meaningful to us to interpret the answer we have there. And that what is that one telling us is that 7056 joules of heat energy is removed every second. And the question is asking us, the second question is asking us to calculate the amount of heat to be removed by refrigerations in a week. So we know the amount of heat to be removed in 1 second. And how do you calculate the amount of heat removed in a week? It's very simple and straightforward. It is all you need to do is to multiply the amount of heat removed in a second by the total time in seconds. Total times, or the total time is seconds. I mean, you have week. Week is it can be converted to seconds. So we know that. How do we do that? We have 7 days in a week, 24 hours in a day, 60 minutes in 1 hour, then 60 seconds in every minute. So you convert the total time in a week to seconds. So this is what we have. So by the time you multiply that, you know the amount of heat to be removed to be this 4267 is 7056, which is the amount we've gotten earlier. Multiply that by the total time in a week. So we have this 4267 for 68800 joules. So this can be expressed in megajoule as 4267.47 megajoules is by dividing this one by 10 raised per 6. This is three zeros and another three zeros. So we have 4267.47 because this is 8, so we can convert that 47, so we can approximate that to 7, so 47 megajoules. So that's the amount of heat to be removed by refrigeration per week. I hope you understand this, and if you have any question, please do not forget to email me at majay@lincoln.ac.uk, and your suggestions will also be welcome. Thank you for listening. Bye.